Okay, what we're going to do here is to explain the notation and start using the words that we're actually going to see in use in the examples after this. First off, this crazy looking function here is called the divergence of f. Of the vector field f. Now why would they call it the divergence? Well, remember when we were coming up with it, what it actually did. It came from this expression where we had our divergence function and it was being multiplied by delta x, delta y, delta z, and the result was equal to the flux out of the box. Right? So this actually makes this a density function. You can multiply this by little tiny volumes and the resulting answer is going to be how fast three-dimensional stuff is coming out of that box. In other words, to diverge just means to move away from. So this measures how fast stuff is actually moving away from the center of the box. In physics, they'll use a different word for this. The charge of a particle. Because it actually measures how fast and how powerfully stuff is actually leaving little tiny boxes, or back then, little tiny spheres that you were actually just putting around the point. So this is actually historically the definition of charge, and this is exactly how they would calculate it. Now, we can either remember it as this, but there's something, a shortcut that's used that will really help when we start talking about Stokes' theorem. So if you look at this, sadly enough, this really looks like a dot product of two strange looking vectors. The first looking vector is going to be the partial with respect to x, the partial with respect to y, and the partial with respect to z. And it looks like we're dotting this with f1, f2, f3. Now, are we really dotting this? No, but we are taking this and putting it next to this, plus this next to this, plus this next to this. And so this is a shorthand way of just remembering it. Now what is f1, f2, f3? That's just our original vector field f. What is this? Well, this is the kind of thing that actually shows up when we were doing gradients, right? Because we would make a vector out of all this kind of thing. So they actually use this kind of notation. They're going to put what looks like an upside down delta, but that's the one we use for gradient. And so this is a symbolism that they're actually going to use for the divergence. It's going to be this vector here. The notation looks like an upside down delta. It's actually called the del operator. You're going to see this in many classes after this, like that. Dot f. So our funny formula, partial f1 with respect to x plus partial f2 with respect to y plus partial f3 with respect to z, is much more customarily just written as delta f, which means our final conclusion is usually written as a triple integral on the right hand side of the divergence with what looks like just an easy way to calculate it. So that's the notation, that's why they call it the divergence, and this is actually a new symbolism we're going to be using as we try to work through some examples.